Hello. We saw a construction for finite fields of order p to the n. The elements of the finite field were all the polynomials over Zp of degree less than n. Addition and multiplication of field elements was performed modulo a reduction polynomial f of x, which is an irreducible polynomial of degree n over Zp. I stated, but didn't prove, that such irreducible polynomials exist for all primes p and all positive integers n. And hence, a finite field of order q exists if and only if q is the power of a prime. I stated, but didn't prove, that all finite fields of the same order q are isomorphic to each other. And this justified calling these fields the Galois field of order q, denoted GFQ. In today's lecture, I'll prove some properties of finite fields. I'll prove what I like to call the frosh's dream. I'll define orders of non-zero field elements, and I'll prove a theorem that generalizes Fermat's little theorem to all finite fields. Lastly, I'll define the notion of generators of the multiplicative group of a finite field. The first property of finite fields I would like to present is what I call the frosh's dream. It says the following: let f be a finite field of characteristic p, and let alpha and beta be arbitrary field elements. Then the binomial alpha plus beta to the power p to the m has a nice expansion as alpha p to the m plus beta p to the m. And this holds for all positive integers m. This is convenient because it makes the binomial expansion really easy to perform. All the annoying terms in the middle are zero. But remember, this only works when the exponent is a power of the characteristic. Let's prove the theorem when m equals 1. By the binomial theorem, we can expand alpha plus beta to the p to get this first term, this last term, and p minus 1 middle terms. Now p choose I is p times p minus 1 up to p minus I plus 1 divided by I factorial. P choose I is an integer, so the numbers in the denominator cancel with numbers in the numerator. When doing this cancellation, the prime number p in the numerator remains uncancelled because p is not a factor of the denominator. And so the integer p choose I is divisible by p, and hence is 0 modulo p. And so this middle term, p choose I, alpha to the I, beta to the p minus I, can be written as a sum of p choose I copies of alpha I, beta to the p minus I. Factoring out alpha to the I, beta p to the I gives us 1 added to itself p choose I times alpha I, beta to the p minus I. Now, since p divides p choose I, and the field has characteristic p, this sum is 0. And so each of these middle terms is 0. And so we've proven that alpha plus beta to the p equals alpha to the p plus beta to the p. The statement for m greater than 1 can then be proven by induction. So this proves the frosh's dream. I'll next tell you about the multiplicative group GFQ star. By definition, the multiplicative group of GFQ is a set of all non-zero elements of GFQ, denoted GFQ star. So here star means non-zero. Here's our main theorem about GFQ star. Let alpha be an element in GFQ star. Then alpha to the q minus 1 equals 1. You might recognize the statement because it's a generalization of Fermat's little theorem from the integers modulo p to arbitrary finite fields GFQ. This is because if GFQ equals the integers modulo p, then q equals p. And so the theorem says that if alpha is a non-zero number between 1 and p minus 1, then alpha to the p minus 1 is congruent to 1 modulo p. The proof of the theorem is similar to one you might have seen for Fermat's little theorem. I'll denote the distinct elements of GFQ star by alpha 1, alpha 2, up to alpha q minus 1. And now we'll consider the elements you obtain by multiplying each of the non-zero elements of the field by the element alpha. This list is also comprised of only non-zero elements. I'll note that these elements are distinct, because if two elements were equal to each other, let's say alpha alpha I equals alpha alpha j, for some I not equal to j, then I can multiply both sides of the equation by alpha inverse, which I do here. I can then cancel the alphas to obtain alpha I equals alpha j. This contradicts the assumption that the elements are distinct. Hence, this list of field elements is just a rearrangement of the set of all q minus 1 non-zero field elements. And so if I multiply the elements in this list together, which I do here, I get the same result as if I multiplied the elements in this list, which I've done here. Finally, canceling alpha 1 from both sides and alpha 2 and alpha q minus 1 gives us alpha to the power q minus 1 equals 1. We have a simple corollary of the theorem which states that for any element alpha in the field GFQ, alpha to the power q equals alpha. When alpha is non-zero, this corollary follows from the theorem simply by multiplying both sides of this equation by alpha. And when alpha equals 0, the statement is clearly true, since both sides are equal to 0. I'll next tell you about orders of field elements. So here's a definition. Let alpha be a non-zero element in GFQ. The order of alpha, denoted ord alpha, is the smallest positive integer t, such that alpha to the power t equals 1. This is an important definition that I'll use in the second half of the course. Let me first note that the order of alpha indeed exists. This is because there is a positive integer such that alpha to the t equals 1, because we could take t to be q minus 1 by the previous theorem which generalized Fermat's little theorem. And so, since a positive integer t exists that satisfies this equation, there exists a smallest such positive integer. And so the order of alpha is well defined. The order of alpha characterizes all powers of alpha which give you 1. So I have this theorem. Let alpha be a non-zero element in GFQ. And suppose that alpha has order t. Then alpha to the s equals 1 if and only if t is a divisor of s. So the only powers of alpha which give you 1 are the integer multiples of t, where t is the order of alpha. Let s be an arbitrary integer. Then long division of s by t yields an equation s equals lt plus r, where L is a quotient, R is a remainder, and R is non-negative, and less than a divisor t. Let me raise alpha to both sides of this equation. So I get alpha to the s equals alpha to the lt plus r, which I'll rewrite in this form. Now alpha to the t equals 1, since t is the order of alpha. And so alpha to the s equals alpha to the r. Hence, alpha to the s equals 1, if and only if alpha to the r equals 1. And since r is a non-negative integer less than t, alpha to the r equals 1 is equivalent to r equals 0. And that's because t is the order of alpha. And finally, r equals 0 is equivalent to saying that t divides s. And that proves our theorem. As a corollary, if alpha is a non-zero element in GFQ, then its order must divide q minus 1. This is because alpha to the q minus 1 equals 1. And the previous theorem tells us that the order of alpha must divide q minus 1. As a quick example, there is only one element in GFQ of order 1, namely the multiplicative identity element 1. And that's because an element alpha of order 1 must satisfy the equation alpha to the 1 equals 1, which of course tells us that alpha equals 1. Here's an example of computing the order of a field element. We'll consider the finite field GF2 cubed, represented as polynomials over Z2 modulo this irreducible cubic. Let's compute the order of the field element alpha, which is x squared plus 1. This is easy to do, because in the example, q, the field order, is 8. So q minus 1 is 7, which is prime. And so the order of alpha must divide 7, and so it's either 1 or 7. But the order of alpha isn't 1, because alpha is not equal to the field element 1. Hence the order of alpha must be 7. Let's do a second example. We'll consider the field GF2 to the 4, represented by polynomials over Z2 modulo this degree 4 irreducible polynomial. Let's verify that this quartic is in fact irreducible over Z2. So first we check that it has no roots in Z2 and thus no linear factors. So we confirm that f of 0 is 1 and f of 1 is also 1. Now we also need to check for the possibility that f has a quadratic factor, because f could have no linear factor, but it could still factor as a product of two irreducible quadratic factors. So I have to make sure that f is not divisible by any irreducible quadratic factors. Now, of the 4 quadratic polynomials over Z2, the first and the third are reducible because they have x as a factor, and the second is also reducible because it has 1 as a root, and therefore x plus 1 as a factor. And you can check that the fourth quadratic is irreducible over Z2 because it has no roots in Z2. And so to complete the verification of the irreducibility of the quartic polynomial f of x, we need to check that f of x is not divisible by this irreducible quadratic polynomial. You can check this for yourself. And so, since f of x has no linear factors and no irreducible quadratic factors, we conclude that f is irreducible over Z2, and so this is indeed a finite field of order 16. Let's find the order of the field element x in GF2 to the 4. We'll do this by computing successive powers of x until we get the element 1. So we have x to the 1 equals x squared is x squared, x cubed is x cubed, x to the 4th is x to the 4th, which leaves a remainder of x plus 1 upon division by the modulus f of x. I'll compute x to the 5th by multiplying both sides of the previous equation by x. So x to the fifth equals x squared plus x. We see that the order of x is not 1, nor 3, nor 5. I know that the order of x must divide 15, because in this example, the field order q is 16, and so q minus 1 is 15. Hence, since the order of x isn't 1, 3, or 5, x must have order 15. Here's a simple fact about the orders of field elements whose proof I'll leave as an exercise. Let alpha be a non-zero element in GFQ with order t. Then, the successive powers of alpha, from the 0th power to the power t minus 1, are distinct. In this list, I stopped at the power t minus 1 because the next element in the list, alpha to the t, is 1, which is the first element in the list. So as you take successive powers of alpha, you cycle through this list forever and ever. In particular, if the order of alpha is q minus 1, which is the largest possible value for the order of alpha, then the elements in this list are the powers of alpha from alpha to the 0 to alpha to the q minus 2. These q minus 1 elements are distinct, and so this set equals the set of all non-zero elements in the field. Such an element alpha is mathematically nice because you can describe all non-zero field elements as powers of alpha. I'll call such elements generators. So a generator of the multiplicative group of GFQ is an element in GFQ of order q minus 1. We saw in the previous slide that the element alpha equals x has order 15 in GF2 to the 4 represented in this way. And so by definition, x is a generator of the multiplicative group of GF2 to the 4. Let's verify this manually by computing all the powers of x to check that the first time we get 1 is at the 15th power. So we have x to the 1 equals x squared, x cubed, x fourth is x plus 1 after subtraction by the modulus. I get x to the fifth by multiplying both sides of the previous equation by x. Similarly, multiplying both sides of this equation by x gives us x to the sixth equals x cubed plus x squared. Multiplying again by x gives us x to the seventh is x to the fourth plus x cubed, which upon subtraction by the modulus gives us x cubed plus x plus 1, and so on. Continuing to multiply both sides of the equation by x, we get the field element 1 for the first time at the 15th power of x. This confirms that x has order 15, and so x is a generator of the multiplicative group of GF2 to the 4. We also see that the powers of x from the 0th power to the 14th power give us all the non-zero elements in GF2 to the 4, namely all the non-zero polynomials over Z2 of degree less than 4. So generators are useful things to have, and they always exist. I have a theorem which states that for every finite field GFQ, the multiplicative group of GFQ has at least one generator. Here's another example, this one with larger parameters. Let's construct the finite field GF2 to the 16. So the characteristic P is 2, and the extension degree n is 16. We need an irreducible polynomial of degree 16 over the integers modulo 2. Let's select f of x to be x to the 16 plus x to the fifth plus x cubed plus x squared plus 1. We haven't developed the tools to efficiently test the irreducibility of high-degree polynomials. So we'll ask Maple to do this for us. And Maple confirms that f is indeed irreducible over Z2. Thus, the set of polynomials of degree at most 15 over Z2 modulo f of x is a finite field of order q equals 2 to the 16, which is 65,536. We can now add and multiply elements in this field. For example, the sum of the field elements A and B is this field element. The product of A and B is this degree 30 polynomial, which leaves this remainder upon division by f. So this is a product of A and B in GF 2 to the 16. Let's now show that the field element x is a generator of the multiplicative group of GF 2 to the 16. So we need to verify that x is order q minus 1, which is 65,535. By the generalization of Fermat's little theorem, we know that the order of x divides q minus 1. Indeed, x to the q minus 1 leaves a remainder of 1 upon division by f. We need to show that the order of x is not a proper divisor of q minus 1. If it were, then the order of x would be missing at least one prime factor, let's say L, of q minus 1. And this means that the order of x would divide q minus 1 divided by L. So we need to show that the order of x doesn't divide q minus 1 over L for all prime factors L of q minus 1. Let's do this. Now the prime factors of 65,535 are 3, 5, 17, and 257. We'll first check that x to the q minus 1 over 3 is not 1 in GF 2 to the 16, and that's true. We'll then check that x to the q minus 1 over 5 isn't 1, x to the q minus 1 over 17 isn't 1, and x to the q minus 1 over 257 isn't 1. So from these four checks, we conclude that the order of x is not a proper divisor of q minus 1, and hence x has order exactly q minus 1. Thus, x is a generator of the multiplicative group of GF 2 to the 16.
So, this concludes the set of lectures on finite fields. We'll need to develop the theory of finite fields a bit more, but we'll save that for future lectures when we need that material. We're ready now to return to studying codes. We'll introduce linear codes in the next video lecture and study some important concepts of linear codes, including the Hamming weight and the generator matrix of a linear code. From V2e onwards, we'll be using a lot of linear algebra in the study of linear codes. We'll see you then.